Okay. So my name is Espen Tallaksen from a company called Bitvis in Norway. I'm going to talk about UVVM, which is a VHDL Testbench architecture, VHDL testbench system. Okay, so briefly, you all probably know that VHDL verification or FPGA verification now is approximately half the time of an FPGA project on average. If you have control-oriented projects or protocol-oriented projects, you'll actually have more than 50% work being verification. But what you might not be that aware of is that out of the time you spend on verification, nearly half of that is spent on debugging. Debugging your design and debugging your test bench. That's extremely important. There's no focus on that. Right, so what is the main scope when you want to verify your device in the test? Of course, you want to verify it with a minimum effort to get a sufficient coverage, pretty obvious. And for that, you have some requirements to your test bench. It has to be simple to write, simple to understand and modify by anyone, and also by yourself 6 months later. It has to be simple to execute, to debug, and to understand what's actually coming out of that test bench in a transcript and a progress report. That's important. This applies to any test bench of any complexity. Now, I want to just briefly mention that we have something called an entry level called utility library, which is a basic VHDL test bench infrastructure. It has logging and verbosity control, alert handling, and extended string handling, simplified randomization. It has the procedures you need to actually check signals coming out of your device in the test. It can check stability on the signal and wait for a signal to be stable, and also wait for change and wait for a value on the signal. All things you do all the time in your test bench. And of course, if you're doing a wait change or wait value, it'll have a window. And if it doesn't find a signal within that window, it'll fail, rather than just waiting forever. So basically, a lot of very simple but very useful functions and procedures. This is not the scope of this talk. I just want to mention it, so because it's really useful and it's dead easy to use, extremely low user threshold. And people tell me that they spend 10 minutes, 15 minutes, maybe they look at the PowerPoint which is available, and they're up and running. And also there's a quick reference which basically shows you all the different commands, and you can go into the details, like in this case, for instance, the check value. You can see all the different overloads, you can see examples, and it's explained properly. So it's easy to get started with that system. Okay, but what I want to talk about is more complex test benches. And for that, I want to look at what actually enables quality and efficiency when you make test benches. It's overview, readability, and simplicity. It's modifiability, maintainability, and extensibility. Debuggability and reusability. This is basically exactly the same requirements as you have for a design. But when you look at people's test benches, it doesn't seem like people know this. But it's pretty obvious. And in order to achieve all this, you have to have a good structure and a good architecture, all the way from the top down to the microarchitecture of your verification environment. So what is required to verify any medium complexity or complex device in the test? Well, of course, you want to provide stimulant interfaces. You want to check the outputs. That's pretty obvious. Then you want to try to reach corner cases, both value and cycle related. And people tend to focus on the value related corner cases, whereas the cycle related corner cases are actually much more difficult to find. That's basically when things happen on the same cycle or a couple of cycles apart. And you have to be able to control multiple interfaces simultaneously. So how should you do this? For a simple device in the test, well, maybe you can just manage with BFMs and these checkers and awaits and so on. But for complex devices in the test, you need more. And what is a UART? Is that a complex device in the test? No, not really. But even for UART, you need to be able to control multiple interfaces simultaneously in order to find cycle-related corner cases. So we have to find a solution for that. So why not look at software, which is a far more mature technology than FPGA. Well, there are issues, in software you issue commands at a high abstraction level. You distribute tasks to the hardware modules, and then basically the software continues and forgets about the commands it has issued. So it controls the hardware outputs, reads the hardware inputs, and configures the hardware behavior of each of the modules in your FPGA or hardware. Then the tasks are handled autonomously inside each of these peripherals. And they scream if something is wrong, basically sending an interrupt to the CPU. Also in software, you have standardized interfaces, standardized protocols, standardized layers, and so on. So basically, software is doing a good job for this. So let's look at this scenario with the hardware-software interface. First, looking at the FPGA there. Then we have the CPU. Of course, the CPU is connected to the FPGA via a bus interface. This calls the processor interface, and which is again, of course, connected to all the modules via an internal bus system in your FPGA. Right? And in this system, you typically have standard interfaces and standard protocols like the Axie4 or Avalon, for instance, or Wishful. So everything is standardized. Then you have inside the CPU, basically what you're doing is having a command sequencer written in software, issuing commands all the time to your hardware and FPGA. Right, so in this system, there's a lot of parallel activity on all these different interfaces, really extremely complex. And software cannot possibly control all of these interfaces and whatever is happening inside here at all times. It's impossible. So that's why it issues commands to these modules so they can actually do the actual work. And that also means that the software and the design harness are totally separated, which enables separate and independent work on the software side and the hardware side. And often, software is a magnitude more work than the FPGA work. So it's important actually that we allow the software system to be as simple as possible and be detached from the hardware. And also, in software, you also have an abstraction layer between this to actually allow even higher level programming. Okay, so let's look at how we can mirror this into our verification system. So first, looking at this system, which I just mentioned, I talked about, I'll look at the FPGA verification environment. Same FPGA, I will now connected a verification component, dedicated, of course, to every single interface, connected directly to each interface. Then we have a test sequencer. And of course, the test sequencer is going to send command to all these verification components. So it needs a bus system to do that. So if now look and compare these systems, just forget about the FPGA in this case, and just compare this verification environment with this hardware-software interface. So basically what we have is these verification components are mirroring basically the peripherals of the hardware. And the test sequencer here is mirroring the test sequencer, basically the software, running on the CPU. And the bus system here is mirroring the Axie, Avalon, Wishbone, whatever. Right. So for both systems, we have a standard module control and status interface, and a standard protocol from the sequencer to the modules, and the standard commands in the sequencer. Of course, I'll come back to how we're standardizing this, but that's basically what we want to achieve. And then we have a mirror the software system, which is a good system. So good, looking at these quality and efficiency enablers, I mentioned these, but there are also some additional stuff which is important to be aware of. So what has reduced the development time the most, and what has improved the quality the most over the last 10 years? So in my opinion, it's IP, right? Design IP. And for that to work, we have to have standard interfaces and standard protocols. Otherwise, it will be very difficult to reuse all these IPs. And of course, another thing is that there are so many users. So that means that we get really fast feedback on any problem in these systems. But these standard interfaces and standard protocols, they are also enablers for efficiency and for quality. So it's extremely important to standardize. So now let's go back to verification. So in my opinion, basically there are three different or main development areas when you make a test bench. One is basically the complete test bench, the test harness, right? The second are the verification modules, verification components. And the third is the central test sequencer. Those are the main elements of any structured test bench. Now, before I dive into these three, I will just show you what we actually do or what this actually means. Because now we have the test case sequencer talking to the verification component, again talking to the bus interface on, in this case, the UART. It's called an SBI on the Discovery VC. SBI stands for Simple Bus Interface. It's just a single cycle bus interface, dead simple. Even simpler than Wishful and Avalon. So let's look at that scenario. And I'll illustrate this with a simple check command from the sequencer. So basically what we do is an SBI check, and this is the command we're going to run. An SBI check, and we're going to check that at this address, we will read this data. Of course, you use constants if you're going to make a good structured test bench. But this is just to illustrate. If we don't read that, it is an error, and this is just a message. And the main idea about this message is that you can use as a comment in your test sequencer, in your test bench. You know what's happening. And as it is a part of this procedure, it can also be printed out in a transcript, which is really good. So anyway, we want to use that or run that command. So the test sequencer is basically sending that command to this address, this target, which is the SBI verification component, instance number 1, because of course there could be many. So it's sending this down to an interpreter. Interpreter receives it, put it into command queue. Command queue says, okay, fine. Interpreter acknowledges the command, and the test sequencer can now continue. Basically exactly the same way as I do for software, where the software just writes a command to a peripheral and forgets about it, and continues. But of course, the peripheral in the hardware will continue to do something after it has been given a command. And the same thing happens here, that an executor will then fetch the command from the command queue and execute that command, a BFM, bus functional model, towards the bus interface over here with that protocol. It will receive the answer, and the check is performed. It doesn't tell the test sequence it has finished. It just does a check, and if the check is okay, it's fine. If it's not okay, then it will send out an alert. And you can also put the result in the result container so that the test sequencer can actually fetch this result later on. Right, going back to these three main levels. The first one was the test harness, right? Which has to be simple. And UVVM is basically Lego-like. And that means when you build a test harness, what we basically do is instantiate the device in the test and verification components. And these are just component-to-component connections in VHDL, as you do in any design, really. Just connect them up. you build a test bench with a test sequencer, instantiate a test harness. Then we include something called verification component methods packages. That basically means that every single verification component has a package of methods and a connection signal. And once the sequencer or test bench includes that package, then you have a connection via packages. It's a global signal in VHDL. And that means you don't need any additional connections from the verification components to the test sequencer because they are basically connected globally. So that means we have a standard global interface throughout the test harness, which means it is dead simple to make, and a standard protocol from the test sequencer to the verification components. Now let's look at the verification components, because you see that the top level is quite easy to understand. So what about verification components? We briefly mentioned them on the previous slide, but let's look at this in slightly more detail. So what actually happens is that you have an interpreter, a command queue, and an executor, as I just mentioned. The interpreter will look, is this command for me? That means, is it for me because I'm now the SPI verification component and I'm instance number n, whatever. Is it for me? If it is for me, is it to be queued? Because if it's to be queued, I'll put it on the queue. And if not, I'll have a case structure, which is quite simple, on what to do, because we have some immediate commands as well. I'll come back to that. Then the executor will get the data command from the command queue, fetch it. It will case on what to do. In the case with the SPI write or SPI check, it basically has 2 or 3 options. Is it an SPI write, is it an SPI check, or an SPI read? Based on that, it will call the relevant BFM and execute that transaction. And that's it. It's that simple. And the good thing is that you have the same main architecture in every single verification component. So 95% same code in the interpreters. It's the same command queue due to the fact that VHDL 2008, you can have a template queue, generic queue. And you have 95% same code in the executors, apart from the BFMs. And of course, the bus functional models you always have to make anyway, unless you're not doing proper verification. So you have a standard verification component internal architecture. And we also provided a script to allow to do generation of verification components. And if you go from a UART BFM, you have the UART BFM, and you want to make a UART verification components, and you don't have any verification component at all, basically you can do that in less than 30 minutes. Dulos did a webinar in April. He said he spent slightly less than 30 minutes, but it was his first time. I do it in 50 minutes. But I've done it before. It's that simple. So once we have this structure, this is now any verification components. Of course, we can add stuff. It's easy, for instance, to add local sequencers, to provide random stimuli, to provide a given sequence of writes and reads, whatever. To add different checkers, like a bitrate checker, frame rate checker, gap checker, whatever, and easily control that. It's easy to handle split transactions. Split transactions is a major problem in many test benches, because basically you're issuing a command. For instance, on Avalon, you're doing a read request command, and then before you get the result back from the device in the test, you may actually issue another command and another one before you get the result back from the first. That's a split transaction. In that case, in this system, it's that simple. Basically, take this queue and executor and copy it down here. Exactly the same queue. And now you have a response executor. So up here, you'll execute the request BFMs, and here you execute the response BFMs. You have to have those anyway. But in this case, it's now structured. Basically, you receive the command, you issue the request BFM, and then immediately pass it down to the queue here, so that this knows that now there's supposed to be a response sometime in the future. I can also have a timeout on that. So we can handle split transactions in a very structured manner. And of course, that also applies for out-of-order execution. The only thing you have to do is basically to change that queue into not a FIFO, but actually somewhere you can actually look into the queue. Look at tags, for instance. So it's a standard queuing system, standard handling of multi-threaded interfaces, split transactions, standard control of parallel checkers. Okay, so next level is the test sequencer. That's the most important part of the test bench because this is where you spend most man hours. It's easy to build the test harness, dead easy, once you have the verification components. And verification components you build for reuse. So in fact, when you have a reusable project, you might actually have everything there, just put in the verification components, or make one or two new verification components. But then of course you want to test different sequences. That's why this is where you spend the most time. Basically the same as with software. You spend most time writing the software sequencer for any embedded system. Must be easy to understand, modify, and maintain, of course. So let's look at the different things we can do in this sequencer. The first thing we talked about is, of course, transactions, right? So apply and check data. So in this case, we're just showing a sequence where you do an SPI write, basically writing into the TX data of the UART, that's the transmit register, telling it to write A0 on the TX output. Then you send a command, a UART expect, to the UART verification component, telling the UART RX part to expect A0, because of course that was what you transmitted, right? Then you can do a UART transmit here. And by the way, when I say UART transmit, I'm talking from the verification point of view. That means from the verification point of view, a UART transmit will be connected to a UART RX on the device in the test, right? In this case, apply A1 on the UART RX, and then you wait for a frame period, UART frame period, and do an SPI check to check that I have actually received an A1. Then I checked all my interfaces. Of course, a very simple scenario, but still, I checked everything. These will all be executed immediately at the same time because these commands are non-time consuming. And that's also a beauty here because that means you can decide exactly when you want to send commands and expect stimuli without having to make really, really complex verification test bench. And this will be done later on because, of course, it needs some time before that appears on this register. Could also been polling, of course, for the flag, but didn't do that here. So this is standard command distribution syntax, standard handling of multiple instances, standard transfer of commands from sequencers to verification components. Next, synchronization. Synchronization is important in any test bench. The worst thing you have in any test bench, any system, is lots of brains that are basically working separately. So, for instance, if you have lots of CPUs, actually aligning them, synchronizing them, is complex. The same applies for a test sequencer. So we have to do that in a proper way, because you can synchronize just by doing a wait value, which is a command in the utility library. You can have a command sent to this verification component immediately, for instance, after sending a write command. You could do an insert delay command before the next write command. In that case, you'll have 2 clock periods break in between those 2 writes. So you can control when you send that or actually execute different transactions. Then you have the main synchronization mechanism in a single sequencer system. And that is to actually tell the UART verification component in this case, I'm going to wait now, the sequence is going to wait for you to complete. So await completion with a timeout. That allows the test sequencer from time to time to actually align with what's happening inside the test harness. So you can do a lot of things and then wait for things to complete. Of course, in some cases, you may need to have multiple sequencers. And for that, you need some more synchronization mechanisms. In this case, you could use a flag or you could use a barrier. Just to make sure that you actually wait for, or one process makes another process wait for the first one, or multiple ones. But it's much better to use this kind of synchronization system because that means you have one single sequencer. But this provides for the fact that some users sometimes want to have multiple sequencers. Again, standard synchronization between any process or verification component, and standard timeout and messaging. The third category basically would be to control the verification components themselves. Could be to flush the command queue, could be to fetch the result, terminate the current command, get last received command index because you want to actually see what that, if you get the last received command index, then you can use that to later retrieve the result on that command index. And then you can also terminate all commands via, for instance, in this case, a broadcast. So in addition to the target specifications, you can also have a multicast and a broadcast. And these are common commands that can be used for any verification components. Standard set again, and a standard way of handling multicast and broadcast. Now, I talked about randomization or corner cases, value-related corner cases. For that, of course, you can use OSVVM, constrained random, and functional coverage. And UVVM and OSVVM can be used as a combined system, where you have the different features from each methodology and library, plus the BFMs and verification components that are provided with UVVM, which is SPI, I2C, UART, and a few more. So these are complementary, giving us what we call a unified VHDL verification methodology. Or in this way, utility library, verification component framework, the randomization and coverage, and the BFMs and verification components. So basically, the OSVM in this case would be a plugin in this system. Looking at how that would work in a real system, if you look at the Testbench verification components, so basically you can have constrained random and functional coverage anywhere in the system. Could be in the test case sequencer, verification components, outside in the device in the test even, and also be anywhere inside the verification components. So they can be combined anywhere. And it can be started and stopped and controlled via sensible commands. So rather than using the UART transmit and some given data, you can use the same command and say, I want to provide random data, 256 of them, and I want to put the result into this buffer. And I can do the same for coverage, to send out a command to say that I want to have received data now with full coverage and put the data into this buffer. So again, standard commands and a standard way of handling this and starting randomization and starting functional coverage. I mentioned debugging as really important. And how do we handle that? Well, as I said, debugging a Testbench is often more work than actually debugging your device in the test. So you have to be able to debug your Testbench as well. So in our system, we can follow the commands through from the test sequencer to execution and automatically print out the logs by just enabling the verbosity you want to have. So in this case, for instance, you can have at this time, this sign here is something that we're using. You can change that if you want to. It's basically saying that at this time, the test sequencer was sending a UART transmit command, right, to this verification component. Sorry. Then, at the same time, just some delta cycles later, the UART verification component will say that, hey, I have received this command. And then the executor will say, yep, I also received it, and I'll execute it. Sometimes later, it will actually be executed, completed. So that means you can follow this through the system. Of course, you can turn these messages off and just see this or that, depending on what you want to see. So again, standardized system, standardized debug structure, and standard debugging control. Yep, these are the verification components and BFMs that are available today. I forgot to add that slide. I also have a roadmap with some other verification components and some more functionality. I won't go into detail on that, but for instance, more on handling constrained random coverage, error injection monitors, more advanced scoreboards. Because today we only use basically the scoreboard is the receiving verification component. So to summarize this, it's basically a Lego-like test harness, reusable verification components, and you can use them, of course, at the module level and FPGA level, and your next project. Reusable verification component structure, which is equally important. Simple synchronization, a clear sequence of events, and that's also important because you can see the complete sequence of event in your test environment by just looking at one single test sequencer, not looking at multiple processes and having to look at when does that start, when is that triggered. Everything is controlled from one single sequencer, if you want that. Of course, as I said, you can also have multiple sequencers. They're easy to understand. If you have some legacy cores, you can easily wrap them to UVVM if you want to, or you can just use them with this system as you like. Just some wishful thinking, in my opinion anyway. I think it would be really great to handle any number of interfaces in a test bench in a structured manner. Reuse major test bench element between module test benches, and also from module test benches to the FPGA test bench. Read the test sequencer almost as pseudocode. Recognize verification spec in what we write in the test sequencer. And understand the sequence event just by looking at the test sequencer, which is really important. And allow simple debugging of test bench and device on the test. So benefits of standardization, it's pretty obvious really. Same simple test bench architecture independent of designer. And when I look at test benches everywhere, most test benches are pure horror, are really terrible. So yes, I've seen good examples as well, but not many. Same VVC architecture independent of designer again, and almost independent of interface. Same commands from one verification component to another, same behavior and response, and even software and hardware designers, DSP designers, whatever, can actually understand and write these sequences. It's easy to make new verification components and for others to use it. Established debug mechanism, same synchronization mechanism between any verification component and any test bench, because that's also normally extremely ad hoc. And easy to reuse major parts of one test bench to another. And it's also easy to share verification components between anyone. That means anyone, independent company. So UVM is gaining momentum. It was released, at least the verification component system was released 1.5 years ago. Great feedback from users. And it was acknowledged as one of two, that is ORCVM and UVM by Julius in the webinar in April. Being used worldwide. And actually extremely new now because just 1 or 2 weeks ago, we were told by ESA that we were given a sponsor. They were sponsoring now the extension of UVM with new features, and they will also recommend their suppliers to use UVM for new deliveries when this is ready, unless of course they have something themselves. I just want to mention this as well. We had a 3-day course on this in Copenhagen, Ankara, and Germany. And I think that's basically it. We want to make better test benches and save time. And it would be really, really great if we could actually start sharing verification components. Not just us providing some few verification components, but having a community actually share verification components. Right. Thank you. Any questions? Is there any hope for a mixed language? Sorry, no. At least there's no plan. No.
Question here. Can you handle integrated component verification? So your design showed like, I don't know, 8, 12 different components with a bus structure connecting all of them. Can you test and verify them all as an integrated whole, perhaps through that bus structure to do so?
What do you mean by an integrated whole?
So, for example, imagine you have an FPGA with a serial port on it, with a HDMI port on it,
Yep.
with an SD-RAM port on it, and eventually the computer is going to attach to all of the above. Can you test all 3 of those components all working together?
Yeah.
That's as an integrated whole.
That's basically the main idea with this system, because you can distribute commands non-time consuming to any number of verification components and then any number of instances of verification components. So you can all start at the same time, or you can skew them. So basically any system.
Are you using the bus to distribute those commands?
Yep. And we're using delta cycles. So you're going to spend some delta cycles to actually distribute them. Yes.
Thank you.
It's more an observation than a question. Are you basically basing the approach on the normal UVM flow of things? I did a course on UVM a long time ago, and a lot of that was very, very familiar.
Yeah.
Sequences, methods, and all this kind of stuff. I think it's great you're doing it for VHDL. I think that's a really, really good idea.
Yeah.
The other question, which again will probably show my ignorance of 2008, does VHDL now have the ability to actually look at low levels of hierarchy of signal values?
All right. Yeah.
Like referral?
First question. Yes, we have definitely looked at UVM. No doubt about it. But we're not making an object-oriented system because VHL is not. But you're trying to make, you're trying to use methods rather than just changing the signals, right? So just trying to use a quasi-oriented, object-oriented approach. But I think the most important thing is that this is component-oriented. And I think hardware designers and VHDL designers are used to thinking about components. So I think it's so much easier to understand a component-oriented system than UVM, because UVM is quite complex. Second question, yes, VHDL 2008 can now dive into the hierarchy and look at anything. Yeah.
Thank you.
Yep.
If I make a change to my Testbench code, do I have to re-elaborate the whole simulator again?
Yes, but it doesn't take much time.
Okay. Depends how big your design is, I guess.
Yeah, but of course, yeah. Yes, but at least in the designs that we have seen and quite a few users, I mean, you're talking about most cases less than a minute, maybe more, but not much.
You just want to use Coco TV?
No, well, I mean, the chip that I'm working on at the moment takes 10 minutes to elaborate. So.
Okay, yeah. Then, of course, it's huge. Yeah. If you make a change to a verification component, you have to do that. And if you make a change to the sequencer, yes, you have to do that. Any other questions?
Yeah. So, just wanted to know a little bit about why you chose to go the open source route and publish the code, encourage collaboration. Kind of why did you go down that path? And perhaps why didn't you then also try to perhaps push these libraries into a bit like what the UVM guys do, I guess, which is is it the who is it that runs UVM Accelerator? Yeah. I mean, are you trying to be the accelerator of the VHDL, equivalent of UVM?
Yeah. Second question first. I don't know the details of that, but it's my impression that Accelerator is not that interested in VHDL, unfortunately. So that's why I think we have to push it ourselves. First question was, Mark, why did we do this?
Yeah.
And the main, basically two reasons for that. One is we use it ourselves in every single project. That's why we made it in the first place. And why did we make it open source? The reason for that is basically marketing. So having done that, our customers sees that we know what we're talking about. We have a system that's actually being used worldwide, so they know that they should come to us when they need help with FPGA design, because we are our design center.
Bragging rights, basically.
Yep.
Yeah.
Yep.
Cool. Fair enough. Is that it? Cool. All right. Well, thank you, Espen.
Yep.
Cheers, mate.
Thank you.